Chapter 7, The Fires of Nuclear Fission, Part 1. In this chapter we want to talk about nuclear fission from a chemistry perspective, address whether or not nuclear energy is safe for humans and the environment, determine if nuclear energy is better, quote unquote, than electric generated energy, and what happens to the waste of nuclear fission. What do you think of when you hear the term nuclear energy? You might think of electrical generation, but you also might think of the negatives, such as the Chernobyl disaster of the 1980s. While performing a safety test, 4 technicians allowed a power surge that reached 120 times the rated capacity of a nuclear reactor. The surge, or what might even be considered slow nuclear explosion, ripped open the core, including the cooling water pipes, and caused a huge steam explosion. The 400-ton concrete enclosure was blown away. 50 different radioactive isotopes were released, and they were shot 1.5 miles into the sky. 150,000 people had to be evacuated from their Ukraine homes, and a radioactive cloud was released over a large part of Europe. It is estimated that 250 million people were exposed to unhealthy amounts of radiation. Estimates of future cancers from the accident range anywhere from 7,500 to 1 million. The city itself still poses a danger with high radiation levels, with pockets of radiation up to 10,000 times higher than normal. It has been almost 30 years since the Chernobyl nuclear reactor exploded, April 26, 1986. This was clearly a devastating accident, and it may lead one to believe we should never consider nuclear power, particularly with the recent disaster in Japan as well. The question in my mind is, can we make nuclear power safer? Is there a way we can achieve that? If so, would the risks in nuclear power plant production outweigh the possible consequences of global warming? We essentially have to do a risk assessment ourselves and look at all the factors to determine what course of action makes the most sense. And it's still being debated to this very day. This is a cover of a magazine called Cosmos, and under the heading of the magazine it says, "Special Report, the Future of Energy, the New Age Nuclear, Clean and Green, the Promises of Thorium." So thorium is a material similar to uranium used in current nuclear power plants. We chose to research uranium and use uranium because it had the potential for weapon production. Thorium is actually a lot safer, and the waste it produces degrades in hundreds of years instead of tens of thousands of years. So perhaps we need to look at some other nuclear options. In this particular lecture, we're going to discuss nuclear power worldwide, how fission produces energy, and how nuclear reactors produce energy. Please take a look at a video on nuclear power and its global use. So you can see that beginning in the 1970s, nuclear power really took off in terms of generating electricity. On the left axis, we have billions of kilowatt hours. On the y-axis. On the x-axis, we have the years 1975 to 2010. And the graph shows in about 1970, we have 100 billion kilowatt hours of electricity generated from nuclear power. And then it begins to peak around 2000, where we have about 750 billion kilowatt hours of electricity produced by nuclear power. And then it kind of plateaus off. And there's not much change between year 2000 and year 2010. And we're continuing to see that trend up through the time this lecture was recorded in 2013. In fact, power plants, the nuclear power plants, are coming to the end of their viability in many regions of the US. They were built 40 years ago, and essentially it would cost too much money to upgrade them, and it would be cheaper for the private companies who own them just to decommission them, and then they have 30 years or so to essentially decontaminate the area and tear down the reactor. This picture shows nuclear power plant locations. We have North America with 123, most of them concentrated on the East Coast. Only 3 in South America, 2 in Africa, really only South Africa. Europe, there are over 203 nuclear power plants, the majority of them, or a large number in France. France gets a significant amount of its energy from nuclear power. Asia has 103. So quite a few spread out over the globe. A significant portion of the globe's energy comes from the electricity generated through nuclear power. Now we're going to do a couple of thinker buddy questions as review. How many protons and how many neutrons are represented by the symbol shown? We have a capital U with 235 in the upper left corner and 92 in the lower left corner. The correct answer is 92 protons. That's our number in the lower left-hand corner, our atomic number. And then the 235 is our atomic mass number. If you wanted to calculate the number of neutrons, you would take that atomic mass number minus the atomic number. In this case, it's 235 minus 92, and that gives us our 143 neutrons. And that little zero sometimes seen above the neutron, or N to represent neutron, just indicates that it has no charge. Protons are positively charged, electrons are negatively charged. Thinker buddy, U-235 and U-238 are examples of A, allotropes of uranium, B, isotopes of uranium, C, isomers of uranium, or D, different elements. B is the correct answer. We often can just discuss different isotopes by including the element symbol and the mass number, because given the elemental symbol, we know if we looked at a periodic table, we could find how many protons there would be, and it would be the same for both. Please take a look at a video on how fission produces energy. So nuclear fission is when you split apart a large atom or nucleus into smaller ones with the release of energy. Energy is released because the sum of the fragments is less than their original mass. Well, then what happened to that mass? What happened to the law of conservation of mass? Just throwing that out the window? We'll talk about that in a moment. This picture shows a nucleus, in this instance split apart by an incoming neutron. And we see it as fragmented into smaller, what we can call fission products, or also daughter isotopes. And it, in the process, is also produced neutrons. Now that missing mass is actually converted into energy and goes out, and it can be harnessed in creating nuclear power or electricity. And this is where you may have heard the famous equation E equals mc squared. We have a picture of Einstein down here. We cannot solve our problems with the same thinking we used when we created them. Albert Einstein. Very true. We really need to shift the manner in which we view our footprint on the world and how we can lessen it. This equation is probably the most important equation of the 20th century. It essentially tells us that energy is related to mass. That if you are able to convert mass into energy, it is actually a very, very large amount of energy. That letter C, if you recall from our investigations of light, represents the speed of light. 3 times 10 to the 8th meters per second. One way to express the energy unit joule is kilograms per meter squared per second squared. So mass is in kilograms, and the speed of light, c squared, ends up giving us meter squared per second squared. So let's look at if we were to take 1 gram of uranium and convert that mass into energy. 1 gram of uranium is 0.001 times 10 to the 3rd kilograms. Let's multiply that by the speed of light squared, which is a constant. We end up with 9 times 10 to the 13th joules of energy. So if you recall, it takes 4 joules of energy to raise 1 gram of water 1 degree Celsius. So say you have water at room temperature, 25 degrees Celsius. It would take about 75 joules to boil a gram of water. Or you could say it would take 750 joules to boil 100 milliliters of water. Now, this 1 gram of uranium would produce 9 times 10 to the 13th joules. If you want to think about how much water that could boil, if we were to do that conversion, we would come up with 120 million liters of water. 120 million liters of water can be brought from room temperature to boiling with the energy released from 1 gram of uranium-235, all of that mass converted to energy. So it just takes a very little amount to get a very significant amount of energy. This energy, if it's used for weapons, you can think of it also as equivalent to 33,000 tons of TNT. And they often refer to nuclear explosions or weapons in terms of the equivalent ton of TNT. And just to give you an idea of what 1 ton of TNT looks like for next to a 6'5" person, it's pretty big. 1 ton of TNT is pretty huge. It makes a pretty big explosion. So 33,000 tons, yeah, that's a lot. That's a lot of energy. So again, if we have something like uranium-238, the mass number is the number of neutrons per plus protons. The atomic number is the number of protons. We generally use our isotopic notation when writing nuclear chemical equations. The reason is we need to show how the mass number has changed, and to be this nuclear equation here shows uranium-235 undergoing fission as initiated by a neutron. So initially it adds, that neutron sticks to the uranium atom, but it's unstable at that point, so it breaks apart. It splits in two. In this case, forming barium-141 and krypton-92, as well as kicking out 3 additional neutrons. Now, these extra neutrons that come out during the fission will be important later on. And I just want to add one more point. Just like any other chemical reaction, we also want to conserve the number of protons and neutrons in a nuclear fission reaction. So here we see one atom of uranium-235 undergoing fissions, producing some daughter isotopes or fission products and releasing 3 other neutrons. And guess what those neutrons can do? Those neutrons can collide with other uranium atoms and initiate fission again and again and again and again and again. If you have enough uranium present, you can start what is called a chain reaction, where just by initiating fission in a few uranium atoms, you can initiate subsequently the fission of other uranium atoms, and the reaction continues without any additional input of neutrons. In a nuclear power plant, what you essentially have is a controlled chain reaction. You start the chain reaction, and then you stop the chain reaction. You start the chain reaction, you stop the chain reaction. In a nuclear weapon, we want the chain reaction to go until essentially as much energy is released as possible in the form of an explosion. Thinker buddy question. Which reaction represents a fission reaction? A. Hydrogen 2 plus hydrogen 3 forms helium 4 plus a neutron plus a gamma ray. That little squiggle is a gamma, and that represents gamma radiation emitted as well. B. Plutonium 234 plus 2 neutrons gives us americium 241 plus a beta particle or an electron plus a gamma ray. C. Uranium 235 plus a neutron gives us rubidium 90 plus cesium 144 plus 2 neutrons plus gamma ray. D. All of the above are fission reactions. C is correct. A, we have 2 hydrogen isotopes combining to form helium. We'll see later that's known as a fusion reaction. B, we see 2 neutrons striking a plutonium-239 atom, but it does not split into 2 smaller isotopes. It forms a larger atom, americium, which has gained 2 neutrons and a proton as well. We'll talk about what type of chemical reaction that is later. So C is correct, where you have a uranium atom, uranium-235, hit by a neutron and splitting into 2 daughter isotopes, releasing 2 additional neutrons and a gamma ray. It doesn't always have to be 3 neutrons released in a fission reaction. Thinker buddy. In the relationship E equals mc squared, the letter m represents A, the mass of the products in a nuclear reaction, B, the mass of the reactants in a nuclear reaction, C, the difference between the sums of the masses of reactants and products in a nuclear reaction, or D, the total of the masses of the reactants and products in a nuclear reaction. C is the correct answer. It's the amount of mass that was lost in the nuclear reaction. That mass that disappeared, quote unquote, was converted to energy. Please watch a video on nuclear reactors. So just to review, a nuclear reactor is one where we have control rods and fuel rods. And basically, by bringing the control rods near the fuel rods, we initiate a controlled chain reaction, essentially. And when we start to get to a certain temperature or release enough heat, we pull apart the rods. That heat is then used to generate steam, which spins a turbine, which generates electricity. So we have two pictures here. On the left, it is the inside of a nuclear reactor core. Looks as if there's some blue light being released from the center. That's where the control rods will interact with the fuel rods, generating the heat. On the right, we have the cooling towers at the Byron nuclear plant in Illinois. Now, an important thing to point out is that this isn't where the reactor core is located. Those are down here in these much smaller buildings. These cooling towers take the steam that was used to spin the turbines and cools it back down to water, so that then when the water is heated, it generates steam, which again spins the turbines. So these are often seen as housing the nuclear reactor, when in fact they just serve one important purpose in generating nuclear energy, but the purpose is to cool the steam in order to reuse it. Thinker buddy. This diagram shows the reactor core in a typical nuclear power plant. What else, in addition to a typical containment building, is there in addition to the reactor core? A. Turbines for feeding steam to the generator. B. Condenser cooling system. C. Water storage tanks. Or D. Steam generators. The correct answer is D. Steam generators are also located in the reactor core. You have the fuel rods and the control rods interacting, producing that heat, and that heat has to be taken away and used to create steam right there at the source of the reactor. All the other components are actually outside of the reactor core. This ends Chapter 7, Part 1.